Hello, my name is Jonathan Magan. This is going to be a recording for both me and my partner for the final project for design of aerospace experiments. In this project, we are going to be basically taking an airfoil, converting it into a 3D wing, and then doing a aerodynamics analysis of it. So calculating the lift coefficient, the drag coefficient, and with varying angles of attack between -5 and 20 with increments of 1. So in order to do this, we first want to upload airfoil coordinates. I have the airfoil coordinates here. Actually, this is not the correct airfoil coordinates. These are the DAT file. You can get these off the airfoil tools database for the Clark Y airfoil. Once you have it in that format, you can go to XFLR5, click File, Open, and sure enough, you'll have your airfoil. Next, you need to go to where is it? Direct analysis. You're going to want to go to analysis and batch analysis. And in batch analysis, you basically want to choose Reynolds numbers that would approximate what you would get on your wing based on its geometry. So just in case, I went from a range of 200,000 to 600,000 with an increment of 10,000. And it's basically going to calculate our graphs based on each of these Reynolds numbers for each of those increments. So I've done that here in the background, as you can see here. Once this is complete, you can then go over to your wing. Click here. In order to design your wing, you just want to go to Plane, Define New Plane, enter your plane name, then go to Define, but I'm actually just going to go back to Current Plane and click Edit, Define, and then because we have a wingspan of 1.5, this is reflected over the y-axis, I believe, or x-axis. And basically this is 0 to 0.75 meters. Multiplied by 2, we get a wingspan of 1.5 meters. Our chord length is going to be 30 centimeters or 0.3 meters. And it's going to be equal across. We don't need any offset here. It's just going to be a standard rectangular wing. And we're using the X-foil that we created in the previous area. So once this is complete, you can just click Save. First you need to double check that your aspect ratio is 5, your taper ratio is 1, and your projected area is 0.45 meters squared. Save. Save. Cancel. All right, so once this is complete, we can go over here and just click Analyze from -5 to 20 angles of attack. Let that work itself out really quick. It says analysis completed. So we'll go to our graphs here. As you can see, we have all of our graphs that are necessary for the project. We have our lift coefficient versus our drag coefficient, our lift coefficient versus our angle of attack, our lift drag coefficient ratios versus angle of attack. And in order to get this data, all you have to do is right-click, click Current Graph, and click Export Graph. You can just tap that, and it will open in an Excel document after you save it. And then you can just plot it in Excel the same way you would with doing the graphs from the previous video or projects I've done in the past. Following this, we need to, in order to calculate your lift slope curve, all you have to do is put these XY coordinates from approximately 10 degrees to -5 degrees and do a trend line across here, and basically just show your equation on the chart. And whatever your equation is, that's going to be the lift slope curve. My apologies. And let me just double check one more thing really quick. In order to get a Reynolds number of 300,000 for this wing, I'm going to go back over here, go to analysis, edit, define. Basically, in order to get the Reynolds number of 300,000, you need a velocity of 15 meters per second for the rectangular wing. That will also vary depending on what wing type you use in your geometry. But for this specific one, yes, you need a velocity of 15 meters per second in order to get over this. So I believe that is going to conclude this part of the project. Once you have your 3-dimensional wing, it's pretty easy from there. You just have to analyze all of your graphs and stuff in Excel and make sure it's professional format. Actually, there is one more thing. I need to go over to our induced drag. And one of the questions in our report asks to find the induced drag at -5 angle of attack, or 5 degrees angle of attack. So we're just going to click the animate button, let that run through really quick until it hits 5 degrees up there. We're going to stop the animate button. And this is our induced drag graph for our wing. So we're just going to right click that, click current graph and export graph. And that'll give you the coordinates to form this graph along its induced drag versus wingspan. Next, you need to also go to current plane. Actually, we're at current graph, then go to define graph settings, and then go to induced angle. And as you can see here at 5 degrees angle of attack, you have a induced angle, kind of maximizing at approximately, looks like -2 degrees-ish along the wingspan. So, and I believe that was the last calculation or last thing that was required for the project. So on that, thank you for watching this video, and the rest of the wings and geometries will be displayed in the final report. Thank you so much for watching.